In this video, we are going to talk about second-degree trig equations. So in the last lesson, we went over how to solve some pretty basic trig equations, and that most of them could be solved with just some basic algebra steps. So isolating the trig function, and then adding and subtracting, multiplying or dividing to solve for your value. In this lesson, we are going to look at second-degree trig equations, meaning that these are going to have a function that is squared. Now, the concept behind it is the same, in that you still want to isolate your trig functions, but in this case, there might be more than one. So you might have, like in this example, where you've got a tan squared and tan. Or in this example, you just have one trig function, but it's squared. So the ideas are the same, and you can think of these a lot like we think of polynomial functions, where you might have something like this equal to 0. Of course, I think I chose something that doesn't factor. Throw that there, where you would then factor and solve from there. So the idea is similar. So if we look at this first example, we've got 2 cosines squared of theta minus 1 equals 0. And we're looking for our solution in degrees and just in the first revolution. So the thing to pay attention to when you have these second degree functions is that sometimes you're going to get more answers, and that's because in this case, when you move the 1 to the other side and then divide by 2, you get that cosine squared theta is equal to 1/2. And when you take the square root, remember that you would get plus or minus, and it would be 1 over root 2 once it's simplified. Now, in order to find this value on our unit circle, we have to rationalize the denominator, and you can see here that this is equal to cosine theta, or gives us a result, cosine theta equals plus or minus root 2 over 2, which we know is at 45 degrees, 135, 225, and 315. And that's because this is plus or minus. So there's an answer in all 4 quadrants. Now, if you look at the next example, this was what I was alluding to before. If you think about this 2 tan squared theta minus tan squared minus 1 equals 0. If you think about this like you would think about this polynomial, if you were solving this, if I asked you to solve this, you would simply factor and like this. So this equals 0. To make sure that's factored correctly, yes. So you would factor it, and then you would say 2x plus 1 equals 0, and x minus 1 equals 0, and you would solve both brackets. Now, we've done so many of these that you might not write out this step. You might right away look at this and know that the solution to this is x equals 1, but the reason that that's the solution, if you go back to when you were first learning about this, is because we're setting each bracket equal to 0. Because if one of these brackets is equal to 0, then this whole equation would be true. And then you would solve for x. So this would be x is negative 1/2, and this would be x equals 1. So we would get 2 solutions. If you use that same rationale, you can factor this function that's got tan in it the same way to get 2 tan theta plus 1 times tan theta minus 1. And when you go and you then break this up into 2 parts, you get that tan theta is equal to negative 1/2, or tan theta is equal to 1. And you can then find these answers either with your calculator or on your unit circle. Now, the thing to watch out for is that when you're working in these instances, sometimes within one question, you might get some values that you might need to use your calculator for, and some values that are going to be on the unit circle. And there can be a mix of both within one question. So in this question, this first factor here, we get tan theta is equal to negative 1/2. Well, tan is equal to 1/2 is not something that's on our unit circle. So using your calculator, you would do tan inverse of 1/2. Remember, we always do the positive so that we get our answer in quadrant 1. But then we know that tan is negative in quadrant 2 and quadrant 4. So we would solve accordingly using the reference angle pi minus 0.464 to get our answer in quadrant 2, and 2 pi, oops, that should say, oh yeah, pi minus, because we're in quadrant 2. It's like 180 minus. And then 2 pi minus 0.464. So remember, in quadrant 2, a lot of the reference angle work that we've done so far has been in degrees. So remember, for a reference angle in quadrant 2, it's 180 minus the reference angle. In radians, it's pi minus the reference angle. In quadrant 3, it's pi plus the reference angle. And in quadrant 4, it's 2 pi minus the reference angle. We spend a lot more time doing reference angles using degrees, so just a little reminder for you. If we look at tan theta equals 1, that's a nice easy one. It's on our unit circle. In quadrant 1, it's where theta is pi by 4, and in quadrant 3, theta is 5 pi by 4. So that's how we would solve that equation. If we look at question C, in question C, we've got 2 cosine squared theta minus cosine theta equals 0. And this is only looking for answers between pi by 2 and 3 pi by 2. So we're only looking for answers on the left-hand side of our unit circle. So in this case, similarly to how you would factor something like x squared minus x equals 0, where you would just take out a common factor of x to get x times x minus 1, that's what we're going to do here. There's no constant term here. So instead, I'm just going to factor out cosine from both terms, and when I do that, I'm left with cosine theta times 2 cos theta minus 1 equals 0. And then I'm going to take each piece, so the first piece, and set it equal to 0. Cosine theta is equal to 0 at pi by 2 and 3 pi by 2, which is just cuts it and making it into this range. And then cosine theta equals 1/2, and those solutions are pi by 3 and 5 pi by 3, which are outside of the given domain. Because cosine is positive, it's only positive in quadrant 1 and 4. These answers are the answers in quadrant 2 and quadrant 3. So as soon as we see cosine is positive, you actually don't even need these values. You know that there will not be an answer within this given domain. If we look at the next one, it's very similar, but in this case, you first have to get all of your terms onto the left side. So tan squared theta, we subtract tan theta, we subtract 6, that equals 0. And then we're going to factor. So this is like x squared minus x minus 6. So tan theta plus 2 times tan theta minus 3 equals 0. And then again, we're going to solve each side separately. So tan theta plus 2 equals 0 would solve or simplify to tan theta equals negative 2. And tan theta minus 3 equals 0 is tan theta equals 3. Neither of these are values from our unit circle, so you're going to plug these into your calculator. So tan inverse of 2, remember, always use the positive value. Make sure that your calculator is set in radians. I should have mentioned that on example B. Make sure your calculator is in radians since that's the units that we're using. And here, tan inverse of 3. So we get our 2 reference angles. Now this first one, tan is negative, so we're going to be in quadrant 2 and quadrant 4. So this will be pi minus 1.107, and 2 pi minus 5.176. And this one we're in quadrant 1 and quadrant 3. So the reference angle is in quadrant 1, and for quadrant 3 you're going to do pi plus 1.249. If we go to the next page, a couple more examples here for you. So this one again, you're going to move the 2 over. I didn't write out that step, but you would have sine squared theta minus sine theta minus 2 equals 0. And then you can factor it. When you factor this, you'll see that you get sine theta is equal to 2 as one solution. Sine and cosine cannot be greater than 1, so this does not have a solution. If you put it in a calculator, you will get an error. On the other side, you get sine theta is equal to negative 1. This is at 3 pi by 2, but if you look at your restriction here, you'll see that there is a restriction that theta has to be between 0 and pi, so 3 pi by 2 would be too large. So this equation with this restriction has no solution. If we look at the next one, we've got secant, which is a reciprocal function, but we still treat it the exact same way. So here, first move the 6 over, then factor. Here you would get secant theta equals 3, but we know that secant is the reciprocal of cos, so this means cosine is 1 over 3, and secant is equal to negative 2. The reciprocal would be cosine theta is equal to negative 1 over 2. And you can solve both of those. Here, cosine of 1/3 is not an exact value, so you're going to put it into your calculator. Again, make sure your calculator is in radians. We get a result of 1.231, and cosine is positive in quadrant 1 and quadrant 4. So I use my reference angle of 1.231 for quadrant 1, and 2 pi minus the reference angle for quadrant 4, and cosine is negative 1 over 2. This is an exact value from the unit circle, 2 pi by 3, and 4 pi by 3. I highly recommend doing lots of practice on these kinds of equations. There's a lot of little tricks and things that can come up. Truly is an example of practice makes perfect for these. Next, we also have general solution. We already talked about general solution when we were talking about our coterminal angles. So far you've seen that all of these solutions have mainly been within the first revolution or half of a revolution, but sometimes you'll be asked for all of the solutions. So you can see if we're asking for all, you're going to either add or subtract 360 times k or 2 pi k. Remember from what we learned before, if k is an integer, we should have that listed there as well, you don't actually need the subtraction because k could either be positive or negative. So just plus 360k or plus 2 pi k, as long as k is defined as an integer, that works. So here if you were solving the equation cosine x equals negative root 2 over 2, where the domain is the set of all real numbers, well, cosine is equal to negative root 2 over 2 at 3 pi by 4 and 5 pi by 4, and then you just add 2 pi k and 2 pi k and make sure that you state that k is an element of the integers. And you should also include these brackets just to denote that this is a set for your solution. If you go to the next page, very similar. In this one, solve the equation that cosine theta is equal to negative 3 over 4, then determine the general solution. Give the solution in radians. So again, you're first going to find your reference angle. This is not on the unit circle, so you're going to use your reference angle here, cosine inverse of 3 over 4. Sorry for the interruption. So we have our reference angle here. of cosine inverse of 3 over 4, which gives us a reference angle of 0.723, but this is negative, so we've got to go into quadrant 2 and quadrant 3. So pi minus the reference angle and pi plus the reference angle. But then the only difference is when you state your solution, you're just going to add plus 2 pi k plus 2 pi k to each of those. And of course, include that k is an element of the integers. The exact same thing is true in example 4. I can already see that in my notes. I forgot to write out the final answer, but here it's already factored for you. So you get cosine theta is equal to 1/3 and sine theta is equal to negative root 3 over 2. So find your reference angle using your calculator, and then we're in quadrant 1 and quadrant 4. And here, these are exact values, quadrant 3 and quadrant 4 from your unit circle. When you state your final answer, you're going to write theta is equal to, and I always go as close to I can in order of the quadrants, so I would start with 1.231 plus 2 pi k, 4 pi over 3 plus 2 pi k. This one, I think this one would come next. It doesn't really matter, but 5.052, my mental math is not quick enough to figure out which one comes next, and then 5 pi by 3 plus 2 pi k, such that, that's what that line means, k is an element of the integers, and close your brackets. So that's how you find the general solution. Like I said a few minutes ago, practice solving these trig equations. They get a lot easier as you try a few, and as always, let me know if you have any questions.